Well, hello everyone. I will present to you my master thesis, and I will talk to you about the horse limb evolution by testing one of the major hypotheses of the side digit reduction, which is the inertial load hypothesis. Oh, why? I cannot change. Sorry. Okay. So, to start with a small introduction, the evolution of horses has been used, and especially of the distal limb, has been used as the textbook example of evolution, of adaptive evolution. And they go from tetradactyl equids with 4 toes to tridactyl ones with 3 toes, with a decrease in the side digit length, and lastly to monodactyl equids with 1 toe. However, we know today with the discovery of more fossils that equid evolution looks more like a tree rather than a straight line. And we know that monodactyl equids and tridactyl equids coexisted for millions of years. Despite that, the trend of side digit reduction is still evident, and we see the loss of side digits in the tribe Equini. So we wanted to understand why we see this trend. Were there any energetic advantages to this change? And here is where the inertial load hypothesis comes in. So it can be summarized as that side digit reduction led to the reduction in the mass at the distal part of the limb, which would decrease the inertial load when swinging the limb, and finally reduce the cost of locomotion for these species. It can be the physics behind this hypothesis can be understood from the equation that you see here from the moment of inertia. But it is more simpler to imagine that if we add weights at the foot or similar weights on our thigh, it is more difficult to swing our limb if the weights are more distally distributed. And that is why the distance, that is because the distance r is greater, and this is multiplied by the mass, and this distance r is also squared. Therefore, based on the inertial load hypothesis, the hypothesis for our study were that when we remove the side digits from tridactyl equids, we expect a reduction in the moment of inertia. And we also expect a generally higher moment of inertia in tridactyl equids compared to the monodactyl ones that is attributed to the increased distal limb mass. To test this hypothesis, we used equids from different parts of the equid phylogenetic tree. On the top, you can see Equus, which is the only surviving genus of equids, and it includes horses, zebras, and asses. And the rest of the equids you see below have different lengths of side digits. To quantify tridactyly, we use the toe reduction index, which is the ratio of side digit length to central digit length based on the proximal pattern, as you see here. And this means that 0 means monodactyly, and the higher the TRI value, the longer the side digits. So we needed to create soft tissue reconstructions in order to calculate the inertial properties of the limbs. First, we mounted the limbs in the mid stance, and then we segmented them based on the muscle insertions on the bones. Then we created convex hull models of each segment, which is the smallest convex shape that includes the osteological segment, and then we merge them all together again. The soft tissue reconstructions for the extant species were validated with 3D models of cadaveric material, as you can see here for the zebra. And as they showed strong and significant correlative results, we use them for the extinct species as well. we segmented these soft tissue reconstructions in functional segments, as you see here, of the hoof, the pastern, the metacarpus, and then the brachium. And we calculated the moment of inertia for their center of mass and about the rotation center as well. But mostly here we will talk about the moment of inertia about the rotation center. So to our results, when we compared the moment of inertia in tridactyl liquids with and without side digits, we saw a decrease in the moment of inertia in the pastern, but a small increase in the metacarpus, despite the decrease in mass that was seen in this segment as well. Lastly, when we took into account the full limb moment of inertia, we saw only small differences between the models with and without side digits, but pairwise comparison of the differences showed significant results. The biological significance of these differences, however, should be further researched. Then we compared the moment of inertia of the tridactyl liquids and monodactyl liquids, and we saw significant differences between those two groups, with tridactyl liquids having a higher moment of inertia. However, we wanted to verify that this is attributed to their side digits. Therefore, we tested each segment separately. And here you can see that in the pastern segment, where we see the side digits, the differences between monodactyl and tridactyl liquids are not significantly different. They are very similar. And that's same for the hoof. And probably the differences we see in the previous graph is due to the metacarpus and endobrachium. We also compared the relative pastern mass between monodactyl and tridactyl liquids, and we didn't see significant differences between the two groups. We also saw an overall increased relative pastern mass in monodactyl liquids compared to earlier highly tridactyl forms. And therefore, we concluded that the side digits did not account for a large amount of mass for the pastern, and probably the enlargement of the central digit was more significant for the monodactyl liquids. All these results show us towards the rejection of our hypothesis, but we still wanted to understand why we see those differences between tridactyl and monodactyl liquids. So we plotted the log of the limb mass to the limb length, and we saw that there are allometric differences between the species. And we see that monodactyl liquids that you see here, the colorful ones mostly, and also Echusandium and Hippidion, plot beneath the isometry line, meaning that they probably had more robust limbs, and they had a lower moment of inertia. In opposite, Protohippus and Cormohipparion that had a higher moment of inertia can be seen above the isometry line. Here is another way to visualize it. The normalized moment of inertia can be seen to decrease with the increased ratio of limb mass to limb length, which means that on the left we can see the more gracile limbs, and on the right the more robust limbs, and the moment of inertia decreases. So to conclude, we rejected the hypothesis that side digits played an important role in the moment of inertia. The decrease we saw in our hypothetical models when we removed the side digits had an only small decrease in mass. Previous studies that have seen a 6.7% increase in the metabolic rate were due to an increase in limb mass of 7.8%. But in our study, with the removal of the side digits, we saw less than 1.9% decrease in limb mass. Lastly, the differences between tridactyl and monodactyl liquids were attributed to allometric differences in segment proportions. There are different reasons why this is observed in horses. Usually the increase in size is associated with more robust limbs. And also the habitat preference is also associated with allometric differences. Uh, Equids that live in more mountainous environments or closed forested environments seem to have more robust limbs, while more slender limbs are associated with open grasslands. All this should be further investigated in more detail, and it is planned for the continuation of this project. And that's it. Thank you very much for your attention.